Today I'm going to be trying something a little bit different. I'm going to be writing as I go with this screen recording. So I'm just screen recording on my iPad and recording on my phone just for hopefully better audio quality than the last video. And I'm also going to try to break each section into smaller points to maybe make it a little bit easier to focus and pay attention and just understand all of the different goals for each day, each section that we're covering. So this chapter is pretty much all about determinants. And so the first section, 4.1.1, is sort of on exploring and motivating a definition of determinants. And due to losing a week of class, we don't quite have time to do that and also get to all of the other important things that we need to get to later this semester. But in lieu of that, I do want to at least motivate the definition a little bit. So, section 4.1.2, we're going to be talking about properties of determinants and motivating the definition a little bit. So, the main question is, how do we tell if a matrix is invertible? And so if I were to just hand you a matrix, so let's say, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, then to tell whether or not this matrix is invertible, you would just do some row operations. And if you can get down to the 3x3 identity matrix, then yeah, you're good. If you can row reduce something to the identity matrix, then yes, it is an invertible matrix because you can do those same row operations to the identity matrix to obtain your inverse, right? So non-singular matrices are the matrices that are row equivalent to the identity matrix, and non-singular and invertible are effectively the same thing. So that's a little bit tedious to do sometimes, especially if we have much larger matrices than 3x3 or something. But first, let me remind you something we talked about before. So 2x2 square matrices are invertible if and only if AD minus BC is not equal to 0. And if we call this matrix A, then we also have a formula for the inverse of A. It is given by 1 over AD minus BC times, so we would switch the diagonal entries and the off diagonals would be made negative. Hopefully I'm remembering this right. But anyway, so yeah, let's double check that that's right. So if I multiply the first row times the first column, I would get A times D plus B times negative C. So we get AD minus BC. And then we're dividing by AD minus BC, so that would be 1. And then if I do the second, so AB times negative BA, that's equal to 0. And so that works for the last two entries as well. So yes, this is our inverse. So in other words, we could check to see if a 2x2 matrix is invertible just by looking at this number right here, AD minus BC. If this number is equal to 0, then it's not invertible, it's a singular matrix. And if it is non-zero, then it is an invertible matrix. And we have a nice formula for the inverse on top of that. So there's not always going to be a simple, easy to remember formula for matrices like there is in this case, but you know, having this number to just check to see if a 2x2 matrix is invertible is nice. So yeah, so the idea, well, okay. So the row operations are the thing that really we want to be utilizing. So we want there to be a number that sort of encapsulates the row operations that you're doing to this matrix to get to the identity. So in a sense, AD minus BC is the number that sort of encapsulates the row operations that take this matrix to the inverse, or sorry, to the identity matrix. Because if you did those row operations to get to the identity matrix, then you would end up having an AD minus BC showing up in each of your factors of the inverse. But anyway, I'm sort of rambling. The point is, the row operations are the thing that really tells us if the matrix is invertible or not. So let me just give you the definition and then we can do some examples. So here's the definition. A determinant function for n by n matrices. So it is just literally a function from n by n matrices to the real numbers, and it satisfies a couple things. So if so the idea is if we do a row operation, then that should change the determinant of your new matrix in some way depending on which row operation you did. So if we add a multiple of a row to a different row, then we're just going to say that that should not change the determinant at all. These are just going to be the same. If A row reduces to B by just multiplying a row of A by some non-zero scalar, actually, this K here could be 0, and we'll see why that's relevant later. But anyway, if we multiply some row of A by any scalar, including 0, then the determinant of the new matrix should be K times the determinant of the old matrix. And if I were to swap two rows, then the determinant of the new matrix that I get should be the negative of the determinant of the old matrix. So just as a also the determinant of the identity matrix is just going to be 1. So we want the determinant of the identity matrix to be 1, so that if you row reduce A to the identity matrix, then you can relate the determinant of your original matrix to the determinant of the identity matrix by, multiplying by scalars and taking negatives at certain points. And yeah, also just as a the following lemma is completely not obvious why this would be true, but determinant functions for n by n matrices are unique. So this is the definition of a determinant function. There might be different functions that satisfy these four properties, but it turns out that 1, there exists such a function for all n by n matrices, and 2, there is only one such function for n by n real matrices that satisfies all this stuff. So let's maybe do an example real quick. Just scroll down here. So let's just pick a random matrix. So let's do 1, 3, 4, 7. Let's do that. So if I were to check using the previous check, I could do I could check to see if AD minus BC is equal to 0 or not. So 1 times 7 minus 3 times 4, this is equal to 7 minus 12, which is negative 5. So that's great. That tells us that this matrix is invertible. Let me move this over here so I can do some row operations. And now let's actually use the definition of the determinant function to see what the determinant of this 2 by 2 matrix should be. So let's row reduce it to the identity matrix. So let's do -4 times row 1, add it to row 2 and replace. So first row stays the same, second one's going to be 0. -12 plus 7 would be -5. Cool. And now I'll do 1 over -5 times row 2, 1, 1, 0, 3. And then I can add, let me move this over a little. And then I'll add -3 row 2, add that to row 1, and I just get my 2 by 2 identity matrix. Okay, so let's figure out, using these row operations, what the determinant is equal to. So this is going to be our matrix A. Here I added a scalar multiple of row 1 to a different row, and in our definition we said that if I add a scalar multiple of a row to a different row, then that should not change the determinant. So what's my determinant over here? Well, it's the same exact determinant as the one before. Okay. Now, if I multiply a certain row by some scalar, then the new determinant should be that scalar times the previous one. So the determinant of this matrix is going to be, let's see if I'm doing this right, it should be -5th of the determinant of the previous matrix. And over here, the determinant of this matrix is just equal to the determinant of A. So like whatever I had over here, I would just like multiply that by -1/5. But anyway, right? And that's using this property right here. If I multiply a row by a scalar, then my new determinant is k times the previous determinant. And then over here, I added a scalar multiple of a row to a different row, and so this does not change the determinant. So the determinant of this matrix is equal to -1/5 times the determinant of A. But it's also equal to 1 because this is the identity matrix, and the determinant of the identity matrix is equal to 1. So that gives us an equation that tells us that -1/5 times the determinant of A is equal to 1. So the determinant of A is equal to -5, which is the same exact thing that we got over here. It's the same thing from our AD minus BC calculation. And so in general, the determinant of ABCD is going to be equal to AD minus BC. This is a general fact. If I were to calculate the determinant of any 2 by 2 matrix, I could do this calculation, or I could just say that it's this using that same work. Okay, let's maybe do a different example. Let's see, maybe I want to go to the previous notes and just pick out the example that I wanted to do. I probably should have copied that over beforehand, to be honest, but yeah, here we go. Let's copy that over. So in the notes, I suggest that you actually try this yourself, and I think at this point in the video, if you feel confident in being able to figure out the determinant of a matrix by yourself, I would encourage you to pause the video and actually try to calculate this determinant. Okay, I'll give you a couple seconds to pause and then figure out what this determinant should be. All right, cool. So let's do it now. Let's go over this. So I have 2, 2, 4, 2, 1, 6, 1, 0, 3, and I have a 1 right here, so I'm going to use that to zero out the entries above it. So I'll do -2 times row 3, add it to row 1, and replace. That won't change our determinant, so that's good. Since this doesn't change the determinant at all, I'm just going to also do that same thing to row 2 to make that a 0 as well. So the determinant of this matrix is going to be the same as the determinant of the matrix I get in the next line, or the next spot. Okay, so we have zeros there. Oh, and this entry is a 0, so that makes this easy because these will just stay the same. So that'll be a 2, that'll be a 1. And now I'm doing -2 times 3 and adding it to these two entries. So -2 times 3 is -6, plus 4 is -2, plus 6, it would be 0. Okay, great. And now I have a 1 right here and a 2 right here. So let's use the 1 to make that 2 a 0. So let's do -2, row 2, add it to row 1 and replace. And I get 0, 0, 1, 0, 3, 1, 0. This will be a 0 now. And because this entry is a 0, that also makes this part easy because this will say -2. Now I will multiply row 1 times -1/2. I get 0, 0, 1. That should be a 3. And then I will add -3 row 1, add it to row 3. And that should, oh, nope, that's wrong. That would not be the identity matrix yet. I have one more step to do. 0, 0, 1, 0, 1, 0, 1, 0, 0. Now I have to swap rows 1 and 3, and then I will get the identity matrix. Okay. Cool. So let's keep track of our determinants. So, okay, here this is going to be our matrix A, right? So here my determinant is still going to be whatever the determinant of A is. Same for this one. I'm just doing that, adding a scalar multiple of a row to another row. Does not change the determinant. And then I will multiply a row by -1/2, so my next determinant should be -1/2 times the previous determinant. Here, my determinant will be -1/2 times the determinant of A, because I'm not changing the determinant at all by doing this row operation. And here, this just changes the sign of my determinant, so here I should get +1/2 times the determinant of A. And since this is the identity matrix, it's also equal to 1. Therefore, the determinant of this matrix A is equal to 1 times 2, so that's 2. Cool. And that's how you do it. Okay, we'll stop that there.